I guess the teachers are new. Okay, cool. So Shapley values try to answer like one particular question, and that is the origin from game theory. And the question is like, how much does each of you actually contribute to the homework assignments, right? So if you work in a group, there's always the people that do all of the work, and there's the ones that are lucky enough to be on the assignment, right? Like, so that's basically how things work. And so Shapley, the person or the researcher, like came up with this. They basically were wondering, okay, so like how can we actually measure this properly? So how much does each individual person contribute to the group assignment or to the team effort or to the team success, right? So and very similar, like we can do this also for features, but let's stick to the team analogy here, right? So let's say we have a team of 4 players and we got like 100 points. That's excellent, right? So now we kind of want to know, like, okay, how much did the red player actually contribute here, right? Because everybody knows, like, the red players are the lazy ones, right? So like we kind of need to figure out like how much did they actually like help in getting, right? So what should be their payout, right? So yeah, so we can just remove the feature and see what we can do instead, right? Like so, but like so we could just remove that person, right, and make the assignment again only with the 3 people, but there's a bunch of problems, right? And in reality, when we talk about features, we cannot just remove the features, right? So we can't do that. So what can we do instead? What do we do in mathematics usually? Nobody? Statistics? What do we do?
Switch it with a neutral feature.
Switch it with a neutral feature? That's an interesting idea. This is something that like you can do if you have a neutral feature or if you know that this exists, right? But like we don't, like in this case, right? So because neutral, even a neutral feature contributes to the team somehow, right? It contributes by not pulling it either side, but it's still better than one that pulls it in the wrong side, right? Like the person in your team is just like, I'll do it, and then like 10 minutes before the deadline, they have not done it, right? So that's a negative one. One that rather does directly say do nothing, then you can work with this, right? So that would be the neutral feature.
So we other teams with red as a member and recognition probability exchange.
What do we call this in statistics? So the answer was like evaluate other teams that have red as a member and then like see how they perform. We call this actually like marginalization. So we basically look at all compositions, right? We look at all possible values of like red in this composition, right? And see like how they would perform. So what we can do is basically we have like our team now, right? Like, so we have like 100, or a score of 100. And then with all of those, with like, let's say a different type of red, right? Like, so like a gentleman type of red and like a glasses type of red and so on, and a mustache type of red, we basically get different payouts. So what we can do then is we can compute what would be the average payout here, right? And then we subtract that and know, okay, so apparently plain red contributed 50 to it, right? So who's happy with that? Like obviously nobody, otherwise I wouldn't ask this way, right? Like, so none of you would be like, okay, this is, so let me ask differently. What's the problem with this approach?
If we do it for every player, we will end up with more than 100.
Like, not sure what you like. So if we do it with every player, it turns out with more than 100.
We have now 50 for that.
Yes.
I think if we do the same calculation for every player, it's not necessary that we will end up with 100 if we need.
That's a very good point. Like, can you phrase it slightly like different? Okay. I think an average, like you will, but like you're onto something, right? So, but like maybe somebody else wants to phrase it in a different way or like have other ideas. Okay, so the first thing is basically that we again creating this nonsensical like combinations, right? So we have like again this Frankenstein samples kind of, right? So we have like really instances that don't exist, so that kind of like can become problematic, right? And the second thing is that it doesn't consider interaction effects. So this is what you're like kind of like we're going towards, right? So just imagine that by having the correct team composition, even though that, for instance, the sunglasses player here contributed to like so badly that we end up with -20. If you have just more team members that have the same vibe, right? Like, and this is just the way they work, and there's less conflict. It might actually be a very valuable team member, right? So the idea here is basically that members contribute more than the sum of their parts, right? So there's interaction effects that lead to a higher payout if they work well together than just like replacing them one by one, right? So like the same player contributes in a different way to different teams, right? Make sense? So that's why this like simple approach unfortunately doesn't work. So what can we do instead? And this is where Shapley values come in. So let's for now assume that we can simply remove a feature. We cannot, it's okay, but let's assume we could, right? So we start with like our 4-player composition here, and then we say, okay, so this would be one version that we would like to evaluate. So we would like to evaluate this one, and then we kind of can say how much red really contributes, right? So we kind of like this will be the marginal contribution of red to the whole team, right? So however, we cannot do this just like for this composition one, we would have to do this for all possible instances, right? So we could do then a measure of like all combinations that are of interest for us, right? So for instance, in this setting, but also what if we have like only a 3-player setup, right? We also need to evaluate how much red contributes in the 3-player setup, right? And then we have, okay, red contribute, like, so we have the, like blue is gone, right? Here, red is there, red is gone. Then we have green is gone, right? And red is there, red is gone. And then we have yellow is gone, and red is there, red is gone. So this way, basically, the reason why we need to do this is to see if there are these interaction effects, right? So what happens with like 2 players are there and 2 players are like they work well together or they don't work well together and so on. Does it make sense? And of course, we have to do this for all combinations, right? So even for the empty set. So what does like basically like happens if there's no team at all? What does that perform, right? And like what does the red player by itself contribute here, right? And with all of this, we can now formulate basically our Shapley loss, or like our Shapley value, actually, not the loss itself. So this looks very intimidating, but we're going to go step by step through this equation, right? So here, var phi m basically is the Shapley value of the feature or the member m. So in our case, always here the red player, right? And then we have like overall m total features. And C minus M or without M is the set of collision does not contain M, right? So for instance, this would be like all the ones where, oh, like you can only see this one here. Oh. This would be all the parts where there is no red player, right? All of those are set M, ZM, sorry. Right? CM. So then like the bars just indicate the size of it, right? So how many like members there are in the set, right? So for instance, for this one, it will be 1, for this one, it will be 2, and for this one, it will be 3, right? Simple as that. And then what this actually is, what this one represents is more like the N over K over all the sets that have basically contain ZM, or the different ways of having a set that has C minus M members, right? Cohen? Right. Yes. And then finally, our top part of the fraction is basically just the contribution with M, right? Like with the red player, and the contribution without the red player for all possible, right? For all possible sets. So this is how this Shapley value is actually produced, right? How it's computed. And again, we will not quiz you on any of these detailed equations and so on, but like something that you have to realize, and hopefully you do very quickly here, is that this is a problem, right? Like computing these values can very quickly become very expensive. Does it make sense? Right? So, but the second thing is, right, because we're basically exponential the number of features. So I should have said that. But the second thing is also like, we cannot actually remove like features, right? So this was the other thing that we just like skimmed over. We said, let's assume we can, but we cannot. So we can solve both these issues through Monte Carlo approaches, right? Or one particular, right? So the idea here is now that we just randomly sample, right? And we have like from a particular data set that we'll describe in a second. But the idea is here now that we basically have like a model. Where are you going? Unbelievable. Okay. So we basically have like 2 different types of data points that we're looking at. And the one is basically some type of x, right? So like our data point, including m, right? Our feature of interest, and some data point without the feature, right? X minus m for each particular x in this case, right? So we generate this by saying that we have another instance, like another feature instance. So we will see this in a second and a bit more depicted, right? But like here to give you some equations. So we have our alternative representation z, right? Or like an alternative sample z, right? And we then randomly select which features go into x with m and which features go into x minus m, right? Some features of x and some features without x. And again, because we do this randomly, but we do this a lot, we sample from it, right? That's why it becomes a Monte Carlo approach, right? Does it make sense? And here, just a circle represents the Hadamard product, or like the element or component-wise multiplication, right? So again, we have our feature vector, or our basically data point of interest, x, right? And we care about feature m. And then we have our z, which is just another sample that we have from our data point, right? And we have those binary masks, which in this case, for instance, 0, 1, 0, right? Which tells us now, okay, which features or which entries do I take from x and which entries do I take from z, right? And then basically we create one version where I take our actual m and one where I take m from z. You have a question? Is it no? Okay. So yeah, but does this make sense? So then we basically in both cases 0, right? So in both cases in this vector we take m with hat, or m with hat, like blue with hat. Then we have a 1. So in both of our new vectors we take our x, so like just plain player, right? Then we have like in both instances like the z value again, because we again have a 0 mask here, and then we have like one times with and once without, right? Because m is the feature of interest. Make sense? Okay. So this is all that basically this says, right? And then we're going to evaluate like the new generated sample with m and the one without m, right? So Shapley values are actually not only like not only useful, but they're actually like fairly unique, right? In the sense that they have a lot of like very, very nice features, very interesting features that make this like a very good way to like analyze your feature importance, right? In this sense. So for instance, like the first one would be efficiency. So the idea here, don't get fooled by like the equation, like or like don't get confused by the equation. It's really what it literally says is that like the sum overall features of the payout has to match what we overall would get, right? So or how we will perform against the baseline, and the baseline being the average, right? So how much better we are than just the average, right? On this x has to match the sum of the Shapley values of the individual features.
How do you get feature? For example, in a high dimensional case such as images, you wouldn't set the single pixel value, right? You would try to do it with a more complex feature. However, how would you define it?
Yeah, so that's a very good point. That's why Shapley values are actually not used, even in this sense, well for high dimensional problems, right? So they're usually used for more like simple dimensional, like lower dimensional problems. To answer your question, what you would do, right, is you would choose one of the features, or like the hidden state of the neural network. Let's say if you have your CNN, right, and at some point there's like this whole understanding that like with the different layers of your CNN, right, or your convolutions, you start to focus on more and more abstract features. So at some point you can basically say like, okay, if we have the last couple layers that make the actual decision, right, let's analyze which features or which outputs in a hidden state contribute to the decision making itself. And then from there, the question now becomes, okay, what is the actual feature, right, that you're matching there? But that's a different question, right? But that's where you use Shapley values in this high dimensional settings. But the other way that you could do is by first abstracting your image into like some other representation, like seeing graphs and so on. And then you do, instead of features, you do nodes and these kind of things, right? Yeah. So the other aspect is the symmetry, basically meaning that like two feature values should be the same, right? If they contribute the same to all possible sets, right? Which is also quite self-explanatory. Dummy is even more intuitive, and that is the idea that if it actually, like if this is a feature that contributes nothing to the payout, the Shapley value has to be 0, right? That's like obviously like also clear. And this one is maybe like it's much clearer than it sounds at first. So the idea of additivity is basically that if you have the Shapley values for like several models, right? And you then combine like computer Shapley values of the linear combination of those models, this will be the same as the linear combination of the Shapley values for the individual models, right? So it's basically f of or phi of let's call, like, what do we call our model? Theta. Phi of theta 1 plus phi of theta 2 plus phi of theta 3 should be equal to phi of theta 1 plus 2 plus 3, right? In a sense. And that's what additivity gives you. Yeah. So again, the interpretation here is really, really neat because it basically tells you like how much does the feature actually contribute to the payout. So that is great, right? And if you consider the model as a game, then like you have the whole like member interpretation and so on, right? But it's not without fault. Welcome back, Paul. I'm just messing with it. It's all good. Okay, so advantage, like that the actual contributions are fairly distributed around the features, right? So there's like we consider things like interaction and these kind of things. So that's really, really great, right? We even can have like contrastive explanations. So basically saying like, what would have happened if that feature would be this, right? So because we can compute the Shapley values for that, right? This kind of thing. And there's a very, very solid theory behind it with like efficiency, symmetry, dummies, and additivity. The disadvantage is that it requires a lot of compute, right? So that's like a big issue. And the second thing is that there is a potential for misinterpretation, right? Because again, what we're analyzing here is how the model, like how much the features contribute to the actual model performance, right? Or to the payout. But this is different from how would the model perform if it would have been trained without that feature. You understand the difference? Okay. So it doesn't mean that like you don't necessarily need this feature for training or whatever, right? Or that you need that feature. So it might be that you get very high Shapley values for like a feature, right? Because it contributes a lot to the payout. But if you actually, like if this feature can be constructed somehow from other existing features, right? Then your model might have been able to perform just as well without that feature. Does this make sense? And yeah, you always need to use all the features. There's no sparse explanation. So it will always tell you like this contributes that much because this contributes this much and this contributes this much and this contributes this much, right? So it's never just a thing by itself. Yeah, and again, like we still have the whole issue with the Frankenstein samples, right? We generate random new samples, so that's always like an issue. So okay, so in order to make this whole thing a bit more tractable, like like any questions so far before we go to the next part? I see I look into a lot of tired eyes. Like, is this post-lunch like depression? What is this? Okay. So Paul, take a note. Next time we're gonna do some waking up exercises. It will be embarrassing for all of us, but at least we'll be awake. Okay. So the idea of SHAP, or SHAP is basically one way of making this whole thing more tractable and so on, is to combine line, like that we talked about in the previous block, and Shapley values together, right? So the idea here is, again, we look into like additive models, like line, for instance, is, right? And so we have our like instance of interest, our x, and we kind of assume that it's a projection into x dash, or like from x dash, right? So that there's like a simpler simpler function, like a simpler input, for instance, a binary vector, right? And like that we can map this binary vector to our x. Important is that this mapping function is specific to x, right? This is not a general mapping function. This is a mapping function that for this instance x, it's able to project like a simplified vector, like a binary vector, into this complex x original vector. Does it make sense? Okay. No? Where did I lose you?
I don't understand what's X dash here. Like we have a model that takes an input X or something. What is X dash here with respect to that model?
Let's do this. So who else, just out of curiosity, who wants me to elaborate on that and was not brave enough to ask? All of you admitted. Okay, but it's easy. So let's do. So thank you very much. Right. So this is a good point. So let's say we have this value here, right? Which is basically like 0.5, 0.7, minus 0.3, minus 0.2, 0.1, and then 0.3, whatever, or minus 0.3. Okay. So let's assume we have this vector, right? And this one has a lot of continuous values. So what I can do now, if I want to represent this as a binary simplified vector, let me do, right? I need to learn a mapping.
Okay.
Right?
So
this will be, for instance, x dash, and this will be x. And it doesn't have to have the same dimensionality, right? So I'm just too lazy to figure out like a nicer example, but even x could even be lower dimensional. X dash could be lower dimensional.
We define x dash by hand or not way.
Doesn't matter at this point, doesn't matter. But there is now this h, right? Like, or in this direction, it would actually be h dash, right? Of x. This gives me x dash. And in this case, it would be x equal h of x dash, right? So this would be in that direction, right? And again, it is something particular to x. So in this case, it basically would be, as you can figure, like here we're just talking about the signs, right? And h would literally just keep the values intact, right? So without any signs. So it literally would just be like 0.5, or like it would be basically h in this case would be like, yeah, sine of x dash times, and then the absolute values here, right? So that's what h would be. It's just like a mapping for this specific example. Okay, where it comes from doesn't matter. And again, it doesn't have to have the same dimensionality or anything like that. It's just that for me, for this purpose, it was simpler to do this way. Okay, so now local methods actually try to ensure, right, that if I now have like some z value, like some z dash, right, which is a different data point in our lower dimensional space, right, and I have x dash, that the local function, or like the function of g of z dash, is somewhere similar to our up projection of the complex model, right? So we have, so if these two are similar, right, then these two should be similar too. That's what it means, right? And then this one is the same as f of, like, so why do we use z here, not x in this equation? Because for x, this is even equal. This is trivial, right? Because h of x dash is just x, and f dash of x, we have that, right? We have that covered. So we actually want to say, like, if we have something like around the vicinity of x dash, right? So z dash, then this still holds. That this will be approximately still the same, right? Make sense? So this is what local methods try to ensure. And then additive ones, we also talked about this at length, right? It's simply the idea that we have basically something like a linear model, right? Or something where we can now have, for instance, our features, and we have like additive weights. Oh, we have weights on it, and then basically our overall prediction is just the sum, like, or the addition of those, right? So we kind of like can always also like write this kind of as an expectation over it. Right? Oh, sorry, the bias or our offset of a local model would be, we would always choose as the average value, right? Which makes sense in terms of the efficiency, right? This is our baseline. Okay. Okay. So some desirable properties that we have here, right? So that basically would be local accuracy, right? So saying that if we have our f of x, right, which is our additive model, then this should also hold for like basically our g of x dash, right? The missingness, so basically if x dash is 0, then the weight should also be 0. So we want to have like the sparseness kind of in there, right? And then the consistency, this seems to be very complicated, but it's actually also, again, similar to the additivity aspects, like much simpler than it looks at first glance. So what this actually says is that if I now have, for instance, where's my cursor? So if I have, for instance, now like the two different models, right? B and A, and basically my difference on one model is larger than the difference on another model, like the difference with respect to Z's with the feature and without the feature, right? Or with a feature and without that particular feature, then the same should also be true for my additive model, or for my weights, actually, in this case, right? So that, yeah, that's basically what a consistency tells you in this case. And the interesting thing is that all of these aspects, because of what we talked about before, like efficiency and additivity and dummy and all of these kind of things, because of those aspects of Shapley values are the actual only like representation, right, that fulfills all three of those properties, right?
Shapley values, we assume that features only have two states. But what if the feature would have three states?
Why would you say features only have two states?
Well, because you can add a feature, like you have the x plus m or the x minus m, right?
Yes, but it does, but the plus and the minus m, right?
Yeah.
They were not without the feature. There were different feature instances. So like the feature is not binary, right? So like if you remember, like our little playing figure, we had like one version with a hat, one with glasses, one with a mustache, and so on, right? So the feature instances are not binary. It's just like, yeah, basically like we compute how much this feature contributes, right, overall, but it doesn't mean that the feature is binary.
Yeah.
Okay. So how does Shep now omit features estimate from or features to estimate the Shapley values from partial data sets? So we basically maintain a background data set, right? So representative of the whole model, right? So like it's important here that when you select your background data set, that it's actually equally sampled from your original data set and not just like, let's say the last 10 data points or whatever, right? Because depending how you collected data science, there might be structure in there, right? So you need to basically have something that is overall representative, right? We create, again, our usual Frankenstein samples that we do, right? So where we basically just like omit features and then like use features from like from other parts of the data set, right? We evaluate all the Frankenstein samples through the model, right? And basically get, this is our new data set. And repeat this for like several sets, right? Like everything that we're interested in. And this way we create now like this new binary permutated data point set, right? These Zs that we mentioned before, and the estimated estimates of the current model output, like gamma I, right? So those are basically, again, this is the same, like a very similar way to creating those Frankenstein data points that we've seen before already, right? So there's like very similar to everything we've done in the permutation and so on features. So yeah, so again with this we basically have our new data set, and that's basically those are the Zs that we'll talk about now, right? So and now what we're trying to do in Shap is that we now fit this like this additive model on those Zs, right? So the Zs are now like this different permutated data set points, right? So when we fit this, I don't have it in here anymore, but oh no, I do. Okay, so we actually, again, this is important, use gamma I and not yi, right? So we actually use like the produced outputs from our Frankenstein data set, right? And just learn this linear model. And we do a weighted linear model in particular in order to actually get Shapley values. So for var phi to be Shapley values, this weighting is very important, right? It has to be exactly that type of weighting. So meaning that the number of data points with the same amount of omitted features, right? The number of features present and the number of features omitted. And you already, just from reading this, you already noticed that this seems very similar to what we've talked about in the computation of the Shapley values, right? Where we have the sets and the sets with it and how many of those there are and so on, right? So this is actually fairly similar. And then if we do optimize this correctly, then we end up with Shapley values, which is the remarkable, like the beautiful aspect here, right? And yeah, and we do this with learned features and so on, and we call this kernel Shap at the end. Okay, so to wrap up here, the advantages and disadvantages of Shap. It's again solid theoretical foundation from Shapley values, right? Inherits all the advantages from Shapley values. It connects Lime and Shapley values together. Although it allows still for global model interpretation, it's a very fast implementation, right? For particular data sets. So for instance, if you have tree representations, you can make very efficient implementations here, right? The disadvantages are that kernel Shap is fairly slow if you don't have these particular data structures, right? And it still ignores feature dependencies, right? And also inherits all disadvantages from Shapley values in general. Okay, so with this, we're done with our second block, and it's again time for 5 and 5. But before that, any questions?
You go a few slides back. There we.
You say stop.
Yes, one more. Yes, stop here. The local accuracy part. How do we get to the x x dash from we have our f x, which is our model, evaluate on an input, but there's no mapping in between to get to the x dash.
Yeah, no. So like the idea is that basically like this is like an equivalency that should hold, right? So basically, because we kind of want to have our local model around our simplified x dash, right? Like the local model around like this simplified vector, right? And that one is computed just as an additive model, like as a linear model, right? And the local accuracy basically means that if I have one particular x and it's mapping x hat, right? And the mapping is given by h. I don't have it in this equation, but we talked about this before, right? Then f of x is the same as g of x dash, right? So that locally, for this mapping from x to x dash, right, the local model produces the same output as the global model or the complex model. That's what it says. Make sense?
Yeah, and at the bottom, to value the z dash as inputs in the big model again.
Yeah, so I did a little bit of a short notation here, right? So the z dash, like fx of z dash is the same of f of h of x of z dash. It's a little bit like to get it into one line, but yes, I should have pointed this out stronger, right? So here's basically like this notation is the same as this notation. So there is the projection that you were missing. Make sense?
Yeah.
Okay, excellent. Thank you so much. Okay, so now 5 and 5. Shall we? Let's go.